Bismillahirrahmanirrahim. Quote of the day is, the elevator to success is out of order. You'll have to use these stairs one step at a time. Assalamu alaikum, everyone. My name is Dr. MOMENA. I am a PGI in Community Medicine Department, and today I'm going to present the topic of counting rules of probability, probability distributions, and binomial distribution under kind supervision of my professor, Dr. Sairab. The agenda of today's meeting will be introduction, counting rules, which include the fundamental rule of counting, the addition rule, permutation, combination, probability distribution types, with special emphasis on binomial distribution, recent advances, and MCQs with key. By the end of this presentation, participants will be able to describe these terms, counting rules of probability, probability distribution, and binomial distribution, and answer the MCQs. First, what is probability? It is the measure of the likelihood or chance that a particular event will occur, expressed as a number between 0 and 1, where 0 means the event is impossible, while 1 means the event is certain, and values in between represent the degrees of uncertainty. The formula is P into E, which represents the probability, is equals to total number of possible outcomes divided by number of favorable outcomes. Now, what are the counting rules of probability? So these rules, they help us count the number of ways an event can occur, which is essential in applying probability formulas. Now we're going to see certain rules along with their formulas, which are used in stats. Number one is fundamental counting rule, also known as a multiplication rule. Now, the fundamental rule is used when you're dealing with a sequence of events or choices which are independent of each other. The rule is, in a sequence of n events, in which the first one has k1 possibilities and the second event has k2 and the third has k3 and so forth, the total number of possibilities of the sequence will be k1 into k2 into k3 and so for kn. In this case, n means to multiply. We'll take an example of tossing a coin and rolling a die. So a coin is tossed and a die is rolled. Find the number of outcomes for the sequence of events. Since the coin can land either heads up or tails up, and since the die can land with any of the 6 numbers showing face up, there are 2 into 6 possibilities, that is equals to 12. A tree diagram can also be drawn for the sequence of events. So this slide shows the tree diagram of 12 possible events. Another example can be taken in which a person can choose from 3 different vaccines and 2 injection sites, arm or thigh. The number of possible combination is 3 into 2 is 6 ways. The other one is the addition rule. So this addition rule occurs when an event is occurring mutually exclusive of the other one. That is, these events cannot occur simultaneously. So this rule is applied. So if event A can occur in m ways and an event B can occur in n ways and they cannot occur together, that is mutually exclusive, then total outcomes is m plus n. We can take an example in which there are 4 males and female doctors and the total number of ways to choose either a male or a female doctor is 4 plus 5 is equals to 9 ways. Moving on to the permutation. In permutation, this rule is mostly applied when the order of selection matters and we are selecting R objects from a set of n distinct objects. So the arrangement of the n objects in a specific order using R objects at a time is called as permutation of n objects taking R objects at a time. It is written as NPR and the formula is as follows. We'll take an example of radio show guests for showing the permutation calculation. So a radio show talk show host can select 3 of 6 special guests for her program. So the order of appearance of the guests is important. How many different ways can this be done? The solution is, since the order of the appearance on the show is important, there are 6p to 3 ways to select the guest. There can be, by using this formula, we have seen 120 different ways to select 3 guests and present them on the program in a specific order. We have put the total number of guests over top and divided by the difference of the number of guests that we can choose from the total number of guests, and then we get 120 as answer. Moving on to the permutation rule number 2, the number of permutations of n objects when R1 objects are identical, R2 objects are identical, and Rp objects are identical. Then we use another modified version of the permutation rule number 2, where R1 plus R2 and so on, Rp is equal to n. There is an example of lateral permutations. How many permutations of a letter can be made from the word statistics? Solution says in the word statistics, there are 3 S, 3 T's, and 2 I's, 1 A and 1 C. We have shown as we have taken all the numbers on the top from 1 to 10 and the number of letters on the bottom and divided and got 50,400 permutations. That can be made from the word statistics. Moving on to the combination rule, it is the number of combinations of R objects selected from N objects and is denoted by NCR, and the formula is given. One important thing about combination rule is these are used when the order or arrangement is not important, as in the selecting process. Example, how many combinations of 4 objects are there if taken 2 at a time? They have said any 2 at a time, no order is given. So we have applied the formula and get a combination of 6. Another example, choosing 2 researchers from a group of 6, applying the values in the formula will get 15 combinations. So this is a summary of a table which shows when to use which type of rule. Tasks in sequence or when the order is mattering, we use the permutation. And if the selection can be done of any object and the order does not matter, we use combination. If the events are happening together, we use the multiplication of the fundamental rule. Or if there is an either or situation, we use the addition rule. This table will help in solving the MCQs, so keep that in mind. Now, moving on to the other part of the presentation is probability distribution. So what is a probability distribution? It is a mathematical function or model that describes how probabilities are assigned to all possible values or range of values of a random variable. It tells us what values a variable can take and how likely each value is to occur in data. There are certain key components. Number 1 is a random variable, which is a variable whose value is the outcome of a random phenomena. This variable can be discrete, which is countable, or it can be continuous, which is measurable. Then there is a probability assignment. For discrete variables, we list each value with its probability. For continuous variables, we define a probability density function, which will be defined later in the slide. And the sum discrete or integral continuous of all probabilities is always equal to 1. Now, there are 2 main types of probability distribution. One is discrete probability distribution, and the other is continuous probability distribution. In discrete probability distribution, we see the values that are countable. For example, 0, 1, 2. They are represented by a probability mass function, PMF. An example include number of dengue cases in a district. The subtypes in this type included are binomial, Poisson, and geometric distributions. Now, what is a probability mass function? It is a function that gives the probability a discrete random variable is exactly equal to some specific value. It assigns a probability to each possible outcome of the variable, and the sum of all probabilities across possible values must equal 1. If x is a discrete random variable, then its PMF is P into Px is equals to x is equals to P into x, where P into x is more than or equal to 0, and sum of all the P is equals to 1. Now, moving on to the continuous probability distribution, the values included in this distribution is any real number within a range, and it is represented by a probability density function, which is also known as PDF. The example includes blood pressure levels in adults. The subtypes are normal, exponential, uniform, normal log, etc. Now, what is a PDF? A probability density function is a function that describes the relative likelihood of a continuous random variable taking on a specific value within a given range. Unlike discrete variables, for continuous random variables, the probability of any single exact value is 0, which is in contradiction with PMF. Instead, this PDF tells us the probability over an interval, and that the area under the curve of the PDF over an interval gives the probability that the variable falls within that range, and the total area under the entire curve of a PDF is always equals to 1. So here lies the difference between PDF and PMF. Now, the examples for a continuous data, like if birth weights in a population follows, we have to use a continuous variable distribution. Here, the subtype of the distribution is shown, which is normal distribution. In case of the discrete variable data, like 20% of a population diabetic, the probability distribution for randomly selecting 0, 1, 2 diabetics in a 5 people sample can be modeled using a continuous variable distribution model, which is binomial distribution here. Now, what is the significance of studying all this in public health? These kind of probability distribution models, they help in understanding the health data, like the number of the new cases of TB or malaria, or understanding the birth weights of the babies. And this is also helps in determining the basis for statistical inferences, like confidence intervals and hypothesis testing and further research. And number third, it determines the type of statistical test to be used. Now, what are the applications? They help in predicting the disease outbreaks. They also help in modeling the survival times, and also help in calculating risks and relative probabilities. Moreover, they help in designing and interpreting the clinical trials and surveys. Now, we have studied the different types of discrete, and we have talked about the different types of discrete and continuous distribution methods. We have binomial, Poisson, and geometric distribution under the heading of discrete variable distribution. And we have normal, exponential, uniform, and log normal under the heading of continuous variable distributions. Moving on to the detail of the binomial distribution. It is applied on binomial experiments. A binomial experiment is also known as a Bernoulli experiment. It is a probability experiment that satisfies the following 4 requirements. Number 1 is there must be a fixed number of trials. Number 2 is each trial can have only 2 outcomes, or outcomes that can be reduced to 2 outcomes. These outcomes can be considered as either success or failure. Number 3 is the outcomes of each trial must be independent of one another. And number 4 is the probability of a success must remain the same for each trial. So if a trial is fulfilling all these 4 requirements, it is said to be a binomial experiment or a Bernoulli trial. Now, what is a binomial distribution? So this binomial distribution is applied on binomial experiments, and it is used when there are only 2 outcomes, like success and failure, with fixed number of trials and constant probability. Parameters: n is the number of trials and p is the probability of success, and k is the random variable. Example: tossing a coin 10 times and counting heads. The formula is as follows. In this formula, n is the number of trials, p is probability, and k is the random variable. So a coin is tossed 3 times, find the probability of getting exactly 2 heads. Solution: this problem can be solved by looking at the sample space. There are 3 ways to get 2 heads. First, in the first event, there are chances of getting 3 heads in all the 3 turns. In the second event, there are chances of getting 2 heads in the first 2 events, and in the last turn, you get a tail. Similarly, head, tail, head, tail, head, head, tail, tail, head, tail, head, tail, head, tail, 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 tail. So these are the events that can occur. So we have to find the 3 times when the head can come. 1, 2, 3. So there are the answer is 3 by 8, or we convert it into decimals as 0.375. We can also use the formula that is given above, and putting the values, we get the answer of 0.375, which is similar to that which is used by the sample spacing. So this is another way of presenting the answer. Another form of binomial distribution is a negative binomial distribution, which is also very important these days. The negative binomial distribution models the number of trials that are needed to get a fixed number of successes in independent Bernoulli trials, where each trial has only 2 outcomes, that is success or failure, and the same probability of success. So here the number of successes, they are fixed, but the number of trials are not. So the key features are each trial is independent. Number two is there are only two outcomes, success or failure. Number three is the probability of success remains constant in every trial. And that is, number four is you're interested in how many total trials are needed to achieve R number of successes. There is an example of example scenario for using this negative binomial distribution. Imagine you're rolling a die and you're interested in counting how many times you need to roll until you get a total of 5 times. Each roll is a Bernoulli trial success if 6 failure otherwise. Getting a 6 has a constant probability, that is, there is a chance of getting the 6 1 by 6. So you want to keep rolling until you get 5 successes. So the total number of rolls or trials needed to get these 5 sixes follows a negative binomial distribution. So this is the formula of the negative binomial distribution, where the capital X is the total number of trials needed to get the R successes, and small r is the number of successes, P is the probability of success on a single try, and small x is the total number of trials, which is equals to or more than or equal to R. Now, why we use a negative binomial distribution? So this model is useful when you're tracking how long it takes for an event to occur multiple times. Number two is events, they are rare but repeated. For example, reinfections, repeated hospitalizations, etc. And number three is it is especially helpful when the variance is greater than the mean. Common in over-dispersed count data. For example, number of emergency visits for asthma in a year. Now, there are certain differences of binomial distribution from negative binomial distribution. In binomial distribution, number of trials are fixed, while in negative binomial distribution, the number of successes are fixed. The number of successes varies in binomial distribution, while number of trials, they vary in negative binomial distribution. The question type in binomial distribution is how many successes in fixed trials, and in negative binomial, how many trials to get fixed successes. So we have talked about binomial distribution. When we are talking about the probability distribution, we also, there are times when we have to calculate mean, variance, and standard deviation. So there are certain revised formulas for these, which are shown here. So the mean, variance, and standard deviation for a binomial variable, they can be found by using the formulas that are shorter but mathematically equivalent formulas. These are shown as follows. Mean is equals to n into p, where n is the number of trials and p is the probability. Variance is equals to n into p into q, where n is the number of trials, p is the probability of success, and q is the probability of failure. And standard deviation is the square root of variance. Now we have an example. A coin is tossed 4 times. Find the mean, variance, and standard deviation of the number of heads that will be obtained. By applying the formulas, we get the values of 2, 1, and 1. 2 mean, 1 variance, and standard deviation as 1. So when 4 coins are tossed many times, the average of the number of the heads that appear is 2, and the standard deviation of the number of heads is 1. So by using this formula, we get these values. And another way of calculating is using the old formulas, not the modified ones, and we get the similar values. So hence the simplified binomial formulas, they can give the same results in this regard. Now, another terminology is used whenever we're talking about the mean of binomial distribution. Another concept is expectation. So this expected value is used in various types of games of chances, insurance, and in the other areas, such as decision theories. The expected value of a discrete random variable of a probability distribution is a theoretical average of the variable. So the formula is summation x into p. So the symbol e into x is used for the expected value. The formula for the expected value is the same as the formula for the theoretical mean. The expected value then is the theoretical mean of the probability distribution. So when expected value problems involving money, it is customary to round the answer to the nearest cent. Now, this is a tabular way of presenting the different types of discrete and continuous variable distribution. We have talked about binomial and negative binomial distribution before. Now we're going to see the other types of distribution and see what key features and examples are involved. Another one is Poisson. So this type of model is used when you want to model the number of events which are occurring within a fixed interval of time or space. So this is very important. When the fixed interval of time or space is mentioned along with the number of events, we have to use this Poisson model. So the examples are calls per hour or arrivals per hour. Another one is geometric distribution, which also falls under the category of discrete This geometric distribution is used to model the number of trials that is needed to get the first success. It is important that the number of trials needed to get the first success in a series of independent Bernoulli trials, yes or no trials. And each trial has the two outcomes which we have already discussed. So geometric somehow resembles the negative binomial distribution, but the difference is in this case we have to get the first success, and in the negative binomial distribution we had the number of fixed trials. Now the example is first success in dice rolling, so this model can be applied in this case. Now for continuous we have normal, exponential, uniform, and log normal. For normal, if we have a normally distributed data, if we plot a graph we get a normally distributed data bell shaped, then we can use a normal distribution or Gaussian distribution on that data. Examples include heights and weights of babies. Number two is exponential distribution. So exponential distribution is used when you are dealing with time between events that happen continuously and independently at a constant average rate. Then this model is used. Example is time to failure. Uniform distribution, equal probability of inclusion is there. Examples include rolling a fair die. Last is log normal. So in this distribution data type is used when skewed data or positively skewed data is being used, but the log of that variable is normally distributed. So we use this type of distribution on that data. Example includes incomes and stock prices. Now moving on to the recent advances. This is the title, Theoretical Framework for the Differences of Two Negative Binomial Distributions and its Application in Comparative Analysis of Sequencing Data. So high throughput sequencing, HTS technologies have been instrumental in investigating biological questions at the bulk and single cell levels. Comparative analysis of two HTS data sets often relies on testing the statistical significance for the difference of two negative binomial distributions, dot and b. Although negative binomial distributions are well studied, the theoretical results for dot and b remains largely unexplored. Here we derive basic analytical results for dot and b and examine its asymptomatic properties. As a state-of-the-art application of dot and b, we introduced dgauge, which is a computational method for detecting differentially expressed genes in single-cell RNA sequencing technique data. dgauge calculates the mean of the sample-wise differences of gene expression levels as the test statistic and determines significant differential expression by comparing the b values with dot and b. dgauge is robust against high dropout levels and exhibits superior sensitivity when applied to balanced and imbalanced data sets, even with small sample sizes. So this shows the importance of the negative binomial distribution in research and in genomic sequencing. Now moving on to the MCQs. Number one is a student wants to create a 3-character password using a combination of letters and digits. The first character must be a letter from A to Z, and second a digit, which will be from 0 to 9, and the third either a letter or a digit. If repetition is allowed, how many different passwords can the student create? A, 26 into 10 into 36, B, 26 into 9 into 35, C, 26 plus 10 plus 36, D, 26 into 10 into 10, E, 36 into 36 into 36.
Alpha.
Yes, alpha is the correct answer. This is the explanation as 26 choices, first character, second character, 10 choices, 0 to 9, third character, a sum of those. And fundamental rule will be applied, 26 into 10 into 36. Number two, a school is forming a 3-member committee from a pool of 10 students. The order in which students are selected does not matter and no student can be selected more than once. Which type of quantum rule should be applied in this situation? A, permutations with replacement. B, combinations without replacement. C, permutations without replacement. D, combinations with replacement. And E, fundamental counting rule. The important point here is order does not matter. Since the order does not matter and the students cannot be selected more than once, then the option B is correct, which is combinations without replacement. 3, a teacher needs to assign first, second, and third prize positions to 3 out of 10 students who performed best in a quiz. Each selected student will get a distinct prize based on their position. What type of counting rule is applicable in this case? A is combination with replacement, B permutation without replacement, C combination without replacement, D fundamental counting rule, and E permutation with replacement.
Permutation without replacement?
Yes, beta is the correct answer, permutation without replacement. For in a class of 40 students, 18 students like mathematics, 15 students like science, and 7 students like both mathematics and science, how many students like either maths or science? Which rule of counting is applied to solve this problem? A, multiplication, B, permutation with replacement, C, addition rule with overlap, D, combination without replacement, E, addition rule without overlap. Yes, Charlie is the correct answer. Addition rule with overlap, since we have students which are liking both of these subjects. So both will show the overlap and either or will point towards the addition rule. This is the explanation. Now, so a healthcare worker is monitoring a dengue outbreak in a rural area. She's entrusted in finding out how many house visits she needs to make until she finds the fourth confirmed dengue case. So the probability of finding a dengue positive case at each house is 0.2 and each visit is independent of the others. Which probability distribution is best suited to model this scenario? A, binomial, B, Poisson, C, negative binomial, D, geometric, and E, normal.
A.
Since we see the probability, sorry,
D.
yes,
Poisson
Charlie
D.
is the correct answer because we have the fixed number of successes. We have to find the fourth confirmed dengue case. Then this is negative binomial distribution. 6. A public health researcher is conducting a survey to assess the success rate of a new vaccine. The vaccine has a success probability of 0.85. That is 85% effective for each individual vaccinated. In a sample of 10 individuals, she is interested in determining the probability that exactly 8 individuals will respond positively to the vaccine. Which of the following distributions would best describe this scenario? A, negative binomial, B, Poisson, C, binomial, D, geometric, E, hypergeometric.
C.
Yes, this is the example of binomial distribution. So a public health instructor is selling a paper for a community medicine exam. Which of the following is the best example of a scenario that he can be included by model of Poisson distribution? A, the number of heads in 10 tosses of a fair coin. B, the number of car accidents occurring at a specific intersection in a day given an average of 3 accidents per day. C, the number of customers waiting in a line at a store during a lunch break, assuming the number is fixed. D, the number of students in a class with a grade greater than 90 on a final exam. And E, the number of pages printed on a printer in a fixed time period, assuming the printing rate is constant.
D.
Yes, beta is the correct answer. 8. A researcher is studying two different types of variables related to the performance of a machine. Number one is the number of faulty parts produced per day, which can take integer values of 0, 1, 2, 3, etc. And number two is the time in hours it takes to complete a maintenance check on the machine, which can take any value within a range, for example, 1.5 hours, 2.3 hours, etc. Which of the following terms best distinguishes the two types of distribution used for these variables? A, identical, B, continuous, C, discrete, D, binomial, E, normal.
D.
Yes, B is correct. 9. A researcher is studying the height of individuals in a population. Heights are measured in centimeters and can take any value within a specified range, which is 160.5 centimeters, 175.2 centimeters. Which of the following terms best describes the type of distribution for height? A, discrete, B, continuous, C, binomials, D, Poisson, E, uniform.
B.
Yes, B is the correct answer. 10. A researcher is studying the following different types of data. Number one, the number of cars passing through our tool booth per minute, which can only take non-negative integer values. 2, the amount of time it takes for a person to finish a marathon, which can be any positive value, 3 hours, 3.5 hours, etc., and the number of defective items in a batch of 100 products, which is an integer value between 0 to 100. Which of the following terms best categorizes the distributions used for these types of data? A, discrete, which is Poisson or binomial. B, continuous normal exponential. C, continuous normal uniform. D, discrete Poisson uniform. And E, mixed discrete and continuous.
E.
Yes, E is the correct answer, most suitable answer, a combination of discrete and continuous. This is the key of the MCQs. These are the references from which the presentation has been made. This is the link of our YouTube channel, and thank you.
Thank you.